Welcome! Let's take a look at finding the value of the limit as x approaches infinity of the quantity 1 plus 1 over x raised to the x power. Now, as x approaches infinity, the base of this function will approach 1 plus and then now 1 divided by increasingly larger and larger numbers. That will approach 0. So we have something that resembles 1 plus 0, or simply 1. Now, that 1 is being raised to the infinity power. So what we have here is an indeterminate form, and our indeterminate form is 1 to the infinity power. So what we need to do is have a strategy that will allow us to deal with this indeterminate form that involves an exponential representation. We need to be able to rewrite that in a form where we can end up with either a quotient that approaches 0 over 0 or a quotient that approaches infinity over infinity. So let's start by simply calling our function y, and y will be 1 over 1 plus x raised to the x power. Now we can use logarithms to turn this exponentiation into a product, and then once we have a product, we can probably take what we have and turn it into a quotient as we need. So let's take the natural log of both sides of this equation. And so we end up with the natural log of y equals the natural log of 1 plus 1 over x to the x power. And then we'll use a property of logarithms to rewrite that as x times the natural log of 1 plus 1 over x. So now we have a product. We still don't have a quotient. So looking at the right-hand side of this equation, I have two possible ways to create a quotient. One would be to rewrite the right-hand side as x over 1 over ln of 1 plus 1 over x. The other being ln of 1 plus 1 over x over 1 over x. So we're going to choose the simpler of these two. So we'll not use the first one, the first option. That's far more complicated. And keep in mind that, in essence, when we move this x to the denominator, we use its reciprocal. So we have the natural log of y equals the natural log of 1 plus 1 over x divided by 1 over x. Now, in case you're concerned about the equivalence of that, recall that when we divide by 1 over x, that's the same or is equivalent to multiplying by its reciprocal. So dividing by 1 over x is equivalent to multiplying by x over 1, or simply multiplying by x. Okay, so now let's consider what's going on with our limit. So we're wanting to allow x approach infinity. So let's look at the limit as x approaches infinity of the natural log of y. That's our new function there. That's the same as the limit as x approaches infinity of the natural log of 1 plus 1 over x, all divided by 1 over x. Now, what kind of form do we have here? Well, as x approaches infinity, my numerator approaches the natural log of 1 plus 0, or the natural log of 1, which is 0. And my denominator, as x approaches infinity, 1 over x, as x approaches infinity, 1 over x approaches 0. So I do have an indeterminate form here, and my indeterminate form is appropriate. It is 0 over 0. So we can go ahead and apply L'Hopital's rule to this limit. So indicating the use of L'Hopital's rule and finding our limit here, or applying it here, we end up with the limit as x approaches infinity. Then we want the derivative of our numerator. Well, we have the natural log of an argument. We have the natural log of 1 plus 1 over x. So the derivative of a natural log is 1 over the argument of that logarithm. So 1 over 1 plus 1 over x. Then we need to multiply that by the derivative of the argument. So the derivative of the inside of the logarithm function will give us 0 plus, and we can think of 1 over x as x to the negative 1 power. So when we take that derivative, we're going to get negative 1 over x squared. And then now we need to take the derivative of our denominator. The derivative of our denominator is the derivative of basically x to the negative 1 power. And the derivative of x to the negative 1 power is negative 1 over x squared. Now we can see that we have this common factor of negative 1 over x squared in the numerator and the denominator. So those will divide out and become a 1. So this and this divide and give us a 1. So we have now the limit as x approaches infinity of 1 over 1 plus 1 over x. Now as x approaches infinity, our numerator remains a 1, and in our denominator, this first term remains a 1 as well. But as x approaches infinity, the 1 over x approaches 0. So we end up with 1 over 1, or just more simply 1. Now, notice that we didn't find the limit of y. Remember, we declared y to be our original function. We found the limit of the natural log of y. So we need to now connect that back to the original limit. So we have the limit as x approaches infinity of the natural log of y. Now, because the natural log of y is a continuous function, that's the same as saying we have the natural log of the limit as x approaches infinity of y. And so we found that that was actually equal to 1. So notice that we declared that the limit as x approaches infinity of the natural log of y, we did this chain of equivalent work and determined that that was equal to 1. Now, in between, we noted that because of the continuous nature of the natural log function, we could switch the order in which we take the natural log and the limit. So now let's go ahead and focus on these last two parts. So we have that the natural log of the limit as x approaches infinity of y is equal to 1. And we can rewrite this in exponential form, or you can consider exponentiating the left and right hand sides of the equation. In either case, we end up with the limit as x approaches infinity of y being equal to e to the first power, or more simply, e. Now, recall that y is the same as our original function. Y is 1 plus 1 over x to the x power. So this limit that we were searching for is actually equal to e. I hope you find this helpful.